So this is the last part of week 15. So this is the final topic, and I congratulate you for making this long. The topic is data path design. So what is meant by data path? Data path basically is all the combinational logic that is used for computational purposes. So for example, if we consider the design of a microprocessor, then ALU, arithmetic logic unit, floating point unit, all the counters and combinational logic, they are part of the data path. So the most important data path element is adder. So let's see how adder works and what are the potential problems in adder and how we can alleviate some of those problems. So we have a half adder here which does not have a carry in, and the truth table is for A is equal to 0, B is equal to 0, C out is 0, sum is 0, and so on. And you know the equations for a half adder are that sum is A XOR B and C out is A and B. So this box is basically A and B. So this is a very simple circuit. If we have A and B, we put an XOR, and the same A and B goes to the AND gate, and we get a C out. So this is a half adder. In a full adder, we have an additional input that is called carry in. Okay, so this is the truth table of carry in, and we know how to compute the equations of S and C out from our basic DLD course. And here we see that C out is basically a majority gate. So C out is the majority of A, B and C, and S is a 3 input XOR gate. Now at the transistor level, things can be optimized, and there can be several implementation, but this is one of the implementation in which we have XOR gates, 3 input XOR gates. So this is 3 input XOR gate, and on the right we have the C out circuit. Okay, the main problem in any adder design is basically the carry propagation. So imagine if you have a 4 input full adder, then every full adder depends upon the previous full adder. So until C1 is produced by FA1, FA2 cannot compute. Until C2 is produced, FA3 cannot compute. So this sort of slows down the whole adder, and the carry propagation is the critical path of the adder. So there have been many works over the years by researchers from academia and also from industry, because this is such an important circuit that the whole ALU boils down to adder design. So this has been rigorously pursued by academia and industry, and there have been many adder designs. Even you can write there are full books out just on the adder design. But here we just will discuss the some of the basic designs, and maybe in the next course on the FPGA design, in the FPGA design course, we will come back to this topic and discuss further types of adders in more detail. So in this slide, one of the approaches shown that what you can do, you can combine both the equations of sum and cout into a single equation, and in this way it is the critical path of the single bit full adder can be reduced, because now you are taking the cout in the middle. So this is one design for a single bit full adder, but most of the time we are interested in multi-bit full adders, not a single bit full adder. So let's see carry propagate adders. A carry propagate adder is a in-bit adder, so it can add in number of bits. So for example, here we have A, which is 4-bit, and B, which is 4-bit, and the carry propagate adder basically allows the carry to go in a ripple fashion from one position to the other position. So I hope that you know how to add numbers. So 1 0, so 1 1 0 1 1 0 1 1 0 1. Okay, and if there is any carry, then you also add the carry. So I think this is from your basic DLD. So here is a 4-bit ripple carry adder. So we just put together different full adders in this fashion, that the cout of one becomes the Cn of the other. So if we talk about this adder, what is the critical path delay? It is basically 4 full adder. In the worst case, you can say 4 full adders. It takes 4 full adder for the carry path to compute. If you don't consider the first full adder, then it is 3 full adder. Okay. So let's define some terms that are used in fast adders. The first term is called generate G. It is basically equal to A and B. And what this means that independent of the carry in input, when generate is 1, the carry out will 1. So whenever G is 1, then we generate a carry. That's why it's called generate. And then propagate, P is A XOR B. So in this case, cout is equal to Cn. So if Cn is 0, cout is 0. If Cn is 1, cout is 1. So that's why it's called propagate. Okay. Then the third one is called kill, or it is basically not of A and not of B. It's the opposite of generate. So whenever kill is 1, so cout is 0 independent of C. So it doesn't matter if Cn is 0 or Cn is 1. When kill is 1, the output cout is always 0. So these are called P, G, K. And these equations can be extended. Okay. So this is the equation of generate. In order to understand this equation, let's draw a figure. So we have I here, J here, and K is here. So these are the bit positions. So capital G, I colon J means the generate from I to J position. This is basically equal to if we propagate a carry from so on this side we have K minus 1. So if G of K minus 1 to J is 1 and propagate is 1, so then we have a generate. Or if I to k is 1. So sorry, let me draw it again. So this is position I. So j I of k, if this is 1, this is j I k, or if k minus 1 is on this side, so k minus 1 up to j, so this is k minus 1 up to j, and p I of k, so if the propagate is 1, then the g is 1. So there are two ways in which g can be 1. Either the g from lower bits multiply by the propagate, or the g from the upper bits. Next is the propagate, which can be, if you are interested in pij, then it is pik dot pki minus 1 up to j. So these are called group generate and group propagate. And the base cases are this. So if you are talking about g of I, it is ai and bi. If you are talking about pi, it is ai exclusive or bi. So at any bit position, if you take the AND, it is called generate. If you take the exclusive OR, this is called propagate. And g of 0 is equal to cn, and p of 0 is equal to 0. So the equation for sum is sum of I is equal to pi exclusive or gi minus 1 down to 0. So this is the equation for sum. This is the whole generate and propagate logic applied to a 4-bit full adder. So we have P0 is equal to 0. So here it is connected to ground. Then we have G0 is equal to Cn. So it is connected to Cn. And then P1 is equal to A1 into B1 exclusive OR. G1 is equal to A1 and B1. So you see all these equations are in the first level and they are called bitwise PG logic. Then the next level is group PG logic, in which the formulas in the previous slides are used. So for G00 you can calculate the formula from the equation given. Similarly for G01, for G02, for G03, you can use the formulas on this slide. Just put in the value of I and J and you can calculate the group PG logic with these equations. The third one is this one, the sum formula. So the sum formula is that the sum at any position is basically Pi. So in this case S1 is equal to C0, which is equal to G00 plus exclusive OR P1. Okay, so in this case Gi minus 1 down to 0 is 1. So we get C0 plus C0 exclusive or P1. Similarly for S2, for S3, you can just use the formula and you can generate the sum terms. Okay, so this is the equations converted to gates. So in the previous slide the gates were not shown. In this slide the gates are shown. So how does it help? It helps basically because the ripple carry is eliminated. First you had to wait for the carry to propagate in ripple carry adder, but now you are generating all the carries in parallel. So this is called carry look ahead adder. Carry look ahead adder calculates all the carries in parallel, and using this group propagate and group generate logic, and then you just need a full adder delay to calculate the whole sum. So we can say that the critical path delay is basically the delay of full adder plus the delay of PG logic. So in this case, if we compare it to the CPD of ripple carry adder, we have reduced it by 2 or 3 times. Then the next data path logic is a comparator. So comparator basically compares 2 things, and it has 3 outputs. So if we have A and B as input, this can be a single bit or it can be in bits, and we have 3 outputs. A is greater than B, A is smaller than B, and A is equal to B. So a comparator is a combinational logic that can tell you if A is greater than B, so this output will be 1. If A is less than B, this output will be 1. And if A is equal to B, this output will be 1. Okay. So you can draw you can design the comparator using the truth table approach. Then the next one is ones and zero detectors. So if you want to detect, for example, if you want to check if all the bits are 0 or all the bits are 1, this has certain applications in computers. So you just want to generate a flag if all are 0 or 1. So you can easily do it with AND gates, and you can optimize the AND gates by replacing them with NAND gates and all these things. So just go through these circuits. Equality comparator. So this is basically XNOR gate. If you want to check if 2 things are equal, just put an XNOR gate. XNOR gate is also called equality gate. So you see this circuit, it's comparing A0, B0, A1, B0, 1, A2, B2, and A3, B3, and you just put an AND gate. So if all the 4 are equal, then this is equal. Okay, if you want to calculate A greater than B or smaller than B, you can use the logic of B minus A. So if B minus A is positive, then B is greater. If it is smaller, then A is greater. So you can use an adder here. Then there are other circuit elements like shifters, which are used for several purposes. So for example, one of the application of shifter is you can multiply by 2 with the shifter. So imagine if we have this number 101, and or let me take another one, for example 0100. So this is basically 4 in decimal. So if I shift it right, it will become 0010. So this has become 2. So a shift right is a division by 2, and a shift left. So if this is 2 and I shift it left, it will become 4. So a shift left is basically multiplication by 2. So we will come back to this shifters and all these things in the next course, when we will be doing fixed point arithmetic. So they are used in ALUs, okay, for different shift operations. Then there is this barrel shifter, which is sort of a universal shifter. It can shift right, it can shift left, or it can rotate. So rotate is basically if you take the this is called shift right and rotate. So you take the final thrown bit and feed it back. So that is rotation. So go through these circuits. They are just multiplexers, and check how they are implementing the right shift and left shift operation. Okay. Then we come to multi-bit, multi-input adders. So again, this is an important topic, and we are just skimming over the details here. I just want to introduce the main concept, and in the next course we will come back to it in great details when we will be doing multiplier design. So why are multi-input adders important? Because they are the core of multipliers. So if you are multiplying two things, the multiplier has three components basically. One is partial product generation, which is basically an AND operation. So imagine if I multiply 1 0 1 and let's say 0 1 0 1. So you see 0 into 1 is 0, 0 into 0 is 0, 0 into 1 is 0, 0, then a space, 1 into 0 1, 1 into 0 0 1 into 1 1, 1 into 1, then two spaces, 0 0 0 0, then three spaces, 0 0 0 0. So you see this partial product generation is basically an AND operation, and this can be done in parallel on all the bits. So this is called PP generation, and then you see there are multiple rows. So this is row 1, this is row 2, this is row 3, and this is row 4. So basically you have to add 4 rows of 4-bit numbers. So this is the multi-input addition, and if you do it using traditional method, and if you allow the carry to propagate, then this will be very slow. So the carry propagation will be over 4 numbers. So people have developed intelligent methods to carry out multi-input addition. One approach is called carry save addition, in which if you add 2 numbers, so let me add 1 1, the result will be 2. So I write it like this: 0 and 1. So 0 is the sum bit and 1 is the carry bit. If I do 1 0, the result will be 1 0. So this is sum bit, this is carry bit. So a carry save adder has 3 inputs and it has 2 outputs. Sometimes this is called a 3 to 2 compressor. Okay, so how this helps with the multiplication, that you can apply the carry save approach to the multi-input additions, and it will compress every 3 rows into 2 rows. So every 3 row will be compressed into 2 rows, and then you combine the 2 rows and apply a carry propagate adder. So this is again multiplicand, multiplier, partial product generation, and these are your multi-input ANDs, and then you add. This is the final product. So again, this is the 6-bit. So these are partial product: x0, y0, x0, y1, x0, y2, x0, y3, x0, y4, x0, y5. So we have how many partial products in a row 6, and how many rows are 1, are 2, are 3, are 4, are 5, are 6. So then we have to add these 6 rows of 6 bits, and here we apply carry save addition. So for example, we take these 3 rows and we convert them into 2. So this one we can drop directly because there is nothing to add. This one we can apply the carry save addition. This one we apply the carry save addition, and these three will be converted into 2. So often we represent these partial products with what is called dot. Okay, and we reduce these dots using the these approaches. So you see that here we have the carry save reduction. Every one of the carry save compressor reduces into 2, and then we finally, when we have finally the result, we apply a carry propagate adder. So a carry propagate adder may be a ripple carry adder, or it can be a carry look ahead adder. So in these two type of adders, the carry is allowed to propagate. So we have the full result in 2 steps. First we apply carry save adder, and finally we apply carry propagate adder. So multipliers uses carry save plus carry propagate adders. In the next course we will discuss several methods of reducing the partial product rows. So there will be more approaches, and we will go into more details. So with this, we come to the end of the course. I hope that you have enjoyed this course, and best of the luck for your finals.